Good morning, friends. It's me, Mr. Reed, again. I hope you are doing well. We are on our second lesson of the week, and today we're going to do a science experiment, a science lesson, all about air. And I want you to think about when you hear the word air, what do you think of? Like, what comes to mind when you think of air? For me, at least, I think of like air conditioning or like hot air or cold air. Like, I always want it to be cold when it's hot outside, or I always want it to be warm air whenever it's cold outside. Or like maybe even I think about wind passing through, right? And so today we're going to talk about maybe how wind forms and also what air might do based upon if it's either what you can see here, cold or hot. So we're going to start off today with a science experiment to get our brains moving. Yesterday we did a game. Today we're going to do a science experiment to get our brains going. Um, when we do this science experiment, I'm going to attach the link to a PDF that you can fill out. It's like got all these different areas that we can fill in. I'm going to try to pull it up afterwards when we get done. You're more than welcome to do it while we do this experiment. But I'm going to show you that. I'm going to try to do better with my video today as well. I know I kind of struggle a little bit on how to do it. Also, by the way, don't forget, I've got my coffee, so I'm ready to teach now. So we're going to get started with what we're going to be doing today. So today, in our science experiment, we're going to test and look at a balloon and how it inflates without me blowing in it. And now I don't know about you, but I don't know how in the world everybody knows how to blow up a balloon. You put the balloon up to your mouth and you blow it up and it gets big, right? But today we're going to see how it might get big, how it might expand without me even touching it. It's going to be completely air. And it is air that you blow into the balloon, but we're going to see what it's like without me blowing air into it. So the first thing I want you to do, or we're going to do, is I have a bottle here. And so, yes, technically you should have a glass bottle. Mr. Reed didn't have a glass bottle. Glass bottles work the best for this science experiment. So if you have a clear glass bottle, that's perfect. You can do this at home. Absolutely. But for the time being, I put some rocks and things inside of this bottle. This is a plastic water bottle. So it'll sink so you can watch it happen. The other things that I have, of course, are this balloon. And then I've got cold water right here. As you can see, I've put some ice in there to prove that this is cold water. I've even put cold over here so you know, okay, this one is the cold water. Over here, I've got hot water. Now, you can't tell that it's hot, but I promise you right now, this water is hot. I just got it out of a Keurig, like a coffee machine. It is hot. And I don't have a temperature gauge to prove it to you, but I promise it is. Okay, so we have cold water and hot water. And what I'm going to do is I'm going to take this balloon. Okay, you can see it's an ordinary balloon, straight up, straight balloon. I'm going to take this balloon and I'm going to set it on top. I'm going to stretch it out and I'm going to stretch it on top of the water bottle. See what? Can you see? I can blow up the balloon if I squeeze the bottle. Okay. But this is a balloon. Okay. The bottle's completely empty except for the rocks. Okay. The rocks are the only thing and it's just for weight. That's the only reason I have rocks in here. And I'm going to stretch it over and it looks limp. There's no pressure in the balloon. Like there's none. This balloon is what? Ready? You want your balloon to do that. You see it's flat. Okay. And here's what we're going to do. This is our cold water. And what we're going to do first is I want you to think, what do you think is going to happen if I place this water bottle in here? What do you think is going to happen with this balloon? Think about that for a second. What do you think is going to happen? Why do you think that might happen? Now, since I'm the teacher, I know what's going to happen. And I know why it's going to happen, but we're going to talk about why here in a little bit. But I'm going to set this water bottle inside this cold water. You can see how it rose. But do you see the water? Is the balloon lifting at all? As a matter of fact, the balloon is still flat. The balloon is still flat. You can see, watch, ready? As a matter of fact, it's even more flat than it was earlier. So yeah, it didn't do anything, huh? Okay, now you're probably thinking, Mr. Reed, how is this a science experiment? You just put a bottle in a cold water and it didn't do anything. And I know that sounds a little silly, But watch what happens now. Would you think about what I might do? What's going to happen if I put this water bottle into the hot water? Think about what is going to happen there? Why do you think that's going to happen? So here we go. I'm going to set it in here. I'm going to take my hands away. Hopefully it works. Let's see here. As you can see, the balloon has lifted all the way to the top. And if I press it, it's kind of firm. I can even bend it over. Watch, ready? It's going to go right back up. Incredible, right? So cool. So I want you to think about, we'll leave it here for a second. I want you to think about what happens. What happened to iterate? No air is escaping that. I mean, there's no air coming out of this water bottle. Where's that air going? But where was the air over here? I want you to think about that as we continue to talk about hot air versus cold air and what they do and how they move and what they're made of and things like that. And so now, to prove it, I'm going to put it back over here into the cold water. And you see, it deflated back. And I'll even prove it one more time. I know I spilled my water. I'm going to prove it one more time. I'm going to take it over here, put it in the hot water. No hands. Miss Reed did not touch it. You can see the balloon is rising. It rose. And then I'm going to take it. Super cool, right? I'm going to take it, put it over here in the cold water. You can even see it's even getting smaller and deflating. So, now that we've talked about that, I'm going to clean it up. Clean up my mess. Mr. Reed made a mess. So if you do this at home, make sure parents know. Mr. Reed said there's going to be a mess, and that is correct. There will be a mess. All right, I'm going to scoot you guys up. Get a little bit closer to me. Put the headphones on just so you can hear me a little bit better. I couldn't do the headphones earlier. So let's see if this helps. I hope this works. Let's see. I'm going to test my video real quick. Yeah. Got it. So we're still going. Perfect. All right. So today, what our objective for the lesson today is that we're going to describe, number one, where wind comes from. And then number two, we're going to identify the two main events that cause wind to occur and the associations that it has with cold and hot air. Okay. So I want us to first think about the temperature. The temperature of gas, what is temperature? Temperature is how hot or cold something is, right? So the temperature of a gas, air is gas, right? We've talked about the three states of matter. What are they? Solid, liquid, and gas. Great job. And so the temperature of a gas measures the speed of what's called molecules. And if y'all don't know what a molecule is, I'll draw a molecule. As a matter of fact, let's see if I can pull up a share screen for a whiteboard. So a molecule is actually what's made of tons of different like elements off of the, what's called the periodic table. But a molecule looks like this. And this is actually what water looks like. Water's called, I wonder if you've ever heard of H2O. So that's two hydrogens and one oxygen. And so this is a hydrogen, this is a hydrogen, and this is an oxygen, right? And so the temperature of a gas measures the speed of how fast these molecules that you see, how fast they're moving. And so what happens is, this is what water's made of, as a matter of fact. And so what's happening, there it is. What's happening is that as the temperature of a gas increases, the molecules begin to move faster. And I want us to think about this in two different ways. When it's warm outside, like it is today, today's really hot, right? It's supposed to be 90 degrees today. When it's warm outside, what do you usually want to go do? When it feels good, right? You want to do what? Go outside and play, right? That's what you want to do. It feels good outside today. I want to go outside and play and run around. And that's what you do, right? You go crazy outside. You run around. Your parents want you to run around. And so when it's warm, you want to move around and go nuts, go crazy. Or I want you to think about it this way too. If you get super full of energy, what do you do? Like, let's say you eat a ton of candy and you get full of energy. What are you going to do? You're going to go crazy. You're going to move around. You're going to be hyper. You're going to be energetic. You're going to go crazy, right? And so this is what these molecules do when the temperature increases. So the warmer the temperature, the more these molecules, these air molecules, move faster. And so this causes the molecules to spread out more. If you have all that energy, you don't want to be confined to one space, right? You want to have everywhere you want to go. And so these molecules spread out. And what these molecules do is they do this thing called thermal expansion. And thermal expansion is one of our vocabulary words today. So thermal expansion. Thermal expansion is a phenomenon in which, whereas temperature increases, molecules move faster. Thermal means heat. Okay, I'll put that in parentheses. Thermal means heat. Okay. So initially, as the gas and air molecules inside and outside of the bottle are the same temperature, the gas molecules inside and both outside are the same, and they're moving at the same speed. But as air molecules collide into the balloon, where can they go? They can only go where? Up, and they've stopped by that balloon. So as the air molecules move up out of that bottle and up, the same energy changes from inside the bottle to up, and they're trying to go outside the bottle because they're like, we need more room, right? And so when the bottle's heated, they move even faster. And so that hot water, as it increased, they move even faster. And these molecules now collide into each other. They're running into each other. Boom, excuse me, right? And they're going crazy. And with more energy means more pressure. And this pressure causes the balloon to expand. So they're moving up and moving up and moving up. So one of the questions I want us to talk about is what's called heat rising. And we're going to question, why does heat rise? Why does hot air rise? Have you ever heard of hot air rises? Think about that. Why though? Why does hot air rise? So the given amount of air, the mass, how much it takes up, right? When it is hot, it takes up more space. So when something's hot, it takes up more space compared to when something is cold. In other words, hot air is less dense than cold air. So any substance that is less dense than the fluid, a liquid or a gas, of its surroundings will float. So for example, let's say you go to the river, or you go to the lake, or you go to the pond. Are there things, is the water always flat? Is it always clear? No, right? What is sometimes floating on the top? You might see a log, right? So what it is that log has less mass. Let me see if I can write that word on here. Clear all my drawings. So mass is the given amount it takes up. So it takes up space. And so the mass of the logs, right? If we have water, right? And we have a log here. This log's mass, even though it possibly might weigh more, the log has less mass and it is less dense than the water. And so this is why the log floats, right? You might even see trash may float. The water bottle will float on top of water. When you see floating things on top of each other, one is less dense than the other. So just as wood floats because it's less than water, hot air floats on cold air because it's less dense. So hot air will always be above cold air. That's why heat rises. Heat rises, heat goes up. I want you to think about any examples. Have you ever heard of hot air rising? When you think of hot air rising, I can think of a really good example of heat rising, hot air something. And it kind of goes along with what experiment I did. I want you to think about this. Well, if you're thinking what I'm thinking, you're thinking of a hot air balloon, right? And so a hot air balloon, see if I can draw one. Hot air balloon, you have a hot air balloon. That was a bad one. Let me try again. Clear all drawings. You have your hot air balloon, right? And you have your people inside of it. Hi, people. He's got a big head, sorry. So you have this hot air balloon. I know it's really weird looking. It almost looks more like an ice cream cone. But what's happening is right here, there's a fire. And this fire pushes hot air up into that balloon. And what does that balloon do? That balloon rises and people ride it, right? I don't know if you've ever been in one. I've never been in one. I almost had an opportunity to go into one. But this is a perfect example. This is how hot air balloons get their lift. That hot air from that fire makes the balloon rise. So that's why hot air rises, because it is less dense, like that word again, dense, D-E-N-S-E, dense than the cold air. So now let's think about wind. This is where we're wrapping up. Let's think about wind. How does the sun, what is our big main energy source of heat? Sun, all right, the sun. And so you have the sun. Let's clear all drawings. So you have the sun up here, right? You have the sun, right? The sun is the big heat source of the entire Earth. And as the relationship between, remember our word thermal expansion from earlier. So once again, thermal. I'll just put EXP. Thermal expansion plus the density, or some people like to say buoyancy. That's a big word. I think since we've been using density is a good word. So when you have the thermal expansion, so think about what is thermal expansion again? And how do you know? It's that moving of the molecules, and as they get more temperature, like higher in temperature or lower in temperature, yeah, as they get higher in temperature, they move more and they need more room to move and they move faster, right? And so then you have density. Density is, the mass of something. If the mass of something that weighs is less, it's going to float on top of the other thing, right? So when you get both of these, this is how wind forms, okay? So the temperature is always doing what? Is the temperature always the same? No, how do you know? Well, yeah, each day is different, right? Today it's 89 degrees, I think. As a matter of fact, tomorrow it's supposed to be 67. What in the world, right? Temperature's always changing. And as different air temperatures near Earth move over vast areas, like literally today and tomorrow, it's perfect. Large bodies of air are either rising or falling. So today's air is going to be rising. Tomorrow's air is going to be falling, which honestly creates rainstorms, which creates clouds. And we've talked about clouds. If you aren't in my class and you're new to my channel, we talked about clouds a couple of weeks ago. My students know what the clouds look like and how they can identify some and how they're formed. We even talked about the water cycle, right? Condensation. And so anyways, as the large bodies of air are rising and falling, air from the surrounding area. So this air, it's either rising or falling, but air from over here is pushed underneath the rising air, or it's pushing out that air, depending on if it's colder, or warmer. This means what must happen to the air? Where does it go? Where's that extra air going? It's getting pushed, right? It's getting pushed out. Air doesn't go away. We know that matter cannot be created or destroyed. And so it's being pushed out. But as the earth rotates in and out of sunlight, we have day and night. As it rotates in and out, different parts of the planet heat up faster than others for several reasons. For example, the land, so the grass and the ground and like rocks get warmer faster than, let's say, water. After a sunny day, you can touch the pavement. Ooh, remember, it is hot. But you might jump in the pool because the pool feels nicer, right? It doesn't get as warm, right? And as a result, the air temperatures over our 7 continents, can you name them? So we have North America, South America, Asia. I'm drawing a blank. Antarctica, Australia, Africa. I'm missing one. Europe. There it is. I got them all. So as the continents, the temperatures over the continents increase more quickly than they do over the oceans and large bodies of water. And so land loses heat faster, though. Land will get colder faster than water will get. And so the angle, that's a math term, the angle at which the sunlight, so this sunlight, let's see if I can come back. I'm going to come back. I'm going to stop share. The angle of the sunlight, it's coming down. The angle of the sun, we saw the sun in that picture. The angle of the sunlight enters the atmosphere. And as the atmosphere affects the amount of heat reaching Earth's surface. And these differences make the Earth warmer. It makes it weather. It makes the weather. It makes it colder or warmer. And it's what makes our weather change and hard to predict. That's why meteorologists are so cool. They know how to predict weather. They try to do their best. And so we see, I want you to also think about, if you go to the lake, if you go to the river, if you go to the pond, or you go to the pool or anything, that air pushing off of that cold, the air pushing off of that water, does it feel good? Oh, yes. I know that when I've gone fishing with Dad, or like it's been a hot day and I'm out at the lake or I'm doing something and I'm just sitting there, people at the beach, and like that air that breeze blows through and you're like, oh my goodness, that felt so good. Right? And so during the day, the land heats up more quick and becomes more warm than the ocean. And so that's why the air above the land expands. The air up here expands, it gets bigger, right? It needs more room to move. And it rises up into the atmosphere, the warmer air does. And we know that the cooler air from above the ocean rushes in to replace it. And that wind is pushing through because that ocean is colder, right? And it pushes through, and that's why it feels so good. And at night, the land loses its heat, right? Because what's gone at night? You guessed it, the sun. So the sun moves through, it loses its heat faster than the ocean does. And as land temperatures fall below what the ocean temperature is, the process is reversed, which makes offshore winds. And offshore winds give the ocean what looks super smooth, when it looks like glass almost. But onshore winds are what makes the ocean make big waves, or white caps. Have you ever seen those? And that's how winds form. You have hot air, you have cold air. So I want you to fill out that hypothesis, that it looks like a comic book kind of sheet for our experiment. If you want, please write me a sentence on how you thought. What are some of your questions? Put them in the comments, anything like that. I miss you guys. I hope you're doing fantastic. I'll come up next week with 2 new science lessons. As a matter of fact, next week's 2 science lessons. They're going to be about changes of matter, specifically heat and how heat changes matter. And we'll dive into that next week. So good to see you guys. Stay safe. Like, comment, subscribe, show your friends. If you're new, once again, so nice to meet you. My name is Mr. Reed from Memphis. Super nice to have you all part of it. Have a great day. Stay safe. Bye, guys.